Hello, this is Mr. Craig, and this is part 2 of day 118. I'm continuing on with half-lives and nuclear decay. This next equation that I'm about to present here isn't on the equation sheet, and I would not expect you to see this on the AP exam. So if you're looking at videos and study for the AP exam, you can stop watching this video. However, this video is very important if you're planning on taking a college entrance exam, which some of you may be reviewing some of these videos to get ready for a college placement exam. And this type of question shows up quite a bit, even though it's not on the AP exam. And this equation is in the middle here, where it has rate. Oops, I probably should go to the reviews button here so I can draw. Deals with rate, and when we talk about rate, this is a rate of decay, and again, for nuclear reactions, do recall that this is a first order reaction. The rate of decay, even though we're talking about half-lives and whatnot, there are what's called the amount of disintegrations per unit of time, and we'll talk about that here in a moment. The rate here talks about that number of disintegrations per unit of time. The K is still a constant, and it's the same constant that we would use in our natural log of the concentrations equals negative K times T. So this K is actually the same K that we're using here, which is very, very nice, because we can find a value for K if we know the rate and the number of disintegrations per unit of time, and use that K to help us answer questions in this equation. So the constant will remain the same regardless of which equation that we're using. And it'll probably make a little more sense once we start doing some of the problems here. And again, the NT is our number of disintegrations, or the number of radioactive nuclei that are undergoing disintegrations or changes or radioactive processes per unit of time. So yeah, again, not for the AP exam, but definitely for if you're getting ready to take a test for college entrance. All right, so let's look at the first example here. It says that iodine-131 is a radioactive isotope of iodine, has a half-life of 8.07 days. A lab worker discovers that a sample of the iodine-131 has been sitting on the shelf for 7 days. The question is, what fraction, or what percent, probably a better question, what percent of the original nuclei is still present after 7 days? Now, we can go ahead and use the equation that we're looking at here, or we can use the equation that we did earlier today, or in the first video for day 118, which again was the mass at some point in time is equal to the mass original times 0.5 of n. And this is a great time to use this equation, because if we were using the one that's in the equation sheet, you're going to have to use anti-natural logs, which is fine, but again, do realize what tools are available for you to use. Now, since we were given the half-life amount of time and how much time the iodine-131 has been sitting on the shelf, we can find out n, and we know not how much we started with, but the question's asking for a fraction or a percent. So let's go ahead and find out how much we have here, or how many half-lives we've gone through. So we haven't gone through a complete half-life yet, so our answer should be over 50%, which we would expect. So we have, again, this is how many. Let me type that in real quick. So 7 divided by 8.07 gives me 0.86. I'm going to leave that number in my calculator. 0.8674. Okay. And that's how many half-lives we've gone through. So we haven't gone through a whole half-life yet. Again, since we're looking for a fraction or a percent, let's go ahead and use a real good number here, like for my mass at some point in t is equal to, let's say I had a 100-gram sample. I just love 100 or 1, but 100 is kind of nice here because we're looking for a fraction here, or percent. So then I'll put in my 0.86, whatever's on my calculator still. Okay, so if I type it in 100 times 0.5 caret, again, hit the answer button. So let's see here, and that will give me 100 times 0.5 to the power of my answer, around 54.8 grams. Okay, so 54.8 grams. And again, to find percent, take what you have. Let's get that just a hair. Times 100%. Okay, so that'll give us 54.8%. Now, I wouldn't look for a fraction on that. That would be kind of ugly. All right, so no biggie with that one. Everybody's good there? Okay. Example number 4. It says that a 2.8 times 10 to negative 6 gram collection of plutonium-238 is decaying at a rate of 1.8 times 10 to the 6 positive value, disintegrations per second. It wants to know what is the decay rate constant for plutonium-238. So again, the equation that we're using here, and hopefully this equation would be given to you if you needed to use it on an exam. That would be kind of mean for them not to give you something like that. All right, well, to find K, what we need to do is we need to take this and move it over so that we have rate over the number of nuclei that's decaying is equal to our K. Well, the rate, we have the rate, which is 1.8, so we have our first part, which is already given to us, so we don't have to do anything to do that. And if you want to call that disintegrations per second, that's okay. So we need to find out our N sub T. So we need to find out how many nuclei are actually changing here. So again, you're given a gram amount, 2.8 times 10 to the negative 6 grams of plutonium, which is element Pu, I'm pretty sure. Yeah, plutonium's Pu. So we need to go to the periodic table and find out. If we're given grams, we need to convert that to, hopefully you said moles. So 1 mole plutonium-238. That's the mass we're using. We're not using the mass that's on the periodic table. This is an isotope, so all the plutonium have a mass of 238. Okay. And then we will convert those grams into nuclei. Okay, so we need to go plutonium, and there's 6.02 times 10 to the 23 nuclei. Okay, then we'll type all that in. And we should get around 7.08 times 10 to the 20, I'm sorry, to the 15. Double check that for me. Yeah, that's 23 minus 6. Yeah, we're good. And that is the number of nuclei that are actually disintegrating. So, nuclei disintegrating or changing. Now, don't get hung up on the word disintegrating in nuclei. So now what I want to do is I want to plug, I have my first part in there. I'm going to put in my second part. And that is nuclei. Okay, actually get rid of that disintegrations. Okay. And then let's type all that in, and my K equals around 2.54 times 10 to the negative 10. And that is per second. Okay, so nuclear disintegrations, yeah, those will cancel there. So we're left with just time. So again, this is my K value, and if I were to ask to find maybe a half-life, I could do that, but this is my constant. So really, we could do some more with this, but that's not what the question's asking. So again, what I needed to do was rearrange. The question was asking for the K, so I needed to get the number of nuclei behind or below the rate here. Solve for K. The rate was given to us, so we didn't have to do anything to solve for that one. And then we had to calculate the number of nuclei that actually would be disintegrated here. Then take those two values and solve for K. All right, let's look at example number 5. I think this is our last one. Oh, yeah, there's a two-parter here. It says if a 0.155 gram sample berkelium 250 has a decay rate, again, our rate's given here, what is the decay constant for the berkelium? So we're going to do the same exact process here that we did up here. So we're going to take our equation and rearrange it so that we have that. So I'm going to go right to that equation. So our rate over n sub t is equal to our k, because if you notice, it's asking for the half-life here, so kind of neat. We have our rate already that was given, and I think that's pretty typical when you will be given a rate. So 1.21 times 10 to the 9, and that's nuclei per second. And again, we always want our K to be some value over a unit of time. And we need to find out how many nuclei we have down here. So we'll, again, grams of berkelium. So we need to convert that to moles. So 1 mole of berkelium. And that's berkelium 250. So we have to use that mass. So you don't need a periodic table for this one. And then 1 mole of berkelium 250, you have Avogadro's number again. And that is the number of nuclei. Okay. Type all that in, and I believe I come up with 3.73 times 10 to the 20, and that is of berkelium 250. All right, so I can plug that in. 3.73 times 10 to the 20 nuclei. Those cancel. And my K is around 3.241 times 10 to the negative 12. Again, nuclei cancel, we're left with 1/2. So there's our K value. And again, that equals K, so there's our constant. Now we get to answer a question with that. So it wants to know what is the half-life for the substance. Again, remember, all nuclear reactions are first-order reactions. So a natural log of 0.5 over the amount that we started with is equal to negative KT. Well, we're looking for the half-life for this, so I'm going to move negative K on down. So I have natural log of 0.5, and I'm going to bring that negative K value over. And what did we say K was? 3.241. 3.421 times 10 to the negative 12. And that's per second. And then when we type all that in, we get 2.14 times 10 to the 11 seconds. So my half-life time is 2.14. Oops. 10 to the 11 seconds. Now I might ask you how many days, how many hours, how many something else that might be. I'm not sure if I've even lived this long. I think I may have been alive this long. All right, so there's your half-life amount of time. And again, if it were to ask you to convert that to days, hours, or something that would mean a little more to us, then we could do that. All right, so I think that's all the examples here for day 118. Again, I hope this has helped, and if you have any questions, do not hesitate to ask.